mistaken, is that correct? 22, okay. And Professor Zhang and I have been co-advising Vedant. He's been doing some interesting work at the intersection of reduced order models, transformers for high dimensional regression problems, and he's going to talk to us about that. Krishna, since you may be joining a CMU thesis proposal for the first time, let me just quickly tell you about the process. So we basically will meet twice. So this is our first meeting, and the second official meeting will be at the defense. We typically do not have intermediate meetings in between the proposal and the defense, but you can always, email us and Vedant if you wanted to meet separately. We can always do this. And at the end of the 45-minute presentation by Vedant, we're going to have some public discussions, and then we're going to have a committee meeting just to discuss the next steps.
Sure.
All right. With that, Vedant, you can.
Hi, everyone. Can you please confirm, Krishna or Amir, if you can hear me? Awesome. Thank you.
I can.
Just hold on one second. Let's get started. Thank you so much, everyone, for coming to my proposal talk. My name is Vedant Puri, and I'll be talking about neural signal representations for computational physics, from reduced order models to scalable transformers. All right, so let me motivate this talk by first discussing the utility of computer simulations in engineering. Across multiple different domains such as automotive engineering and civil engineering, we use computer simulations to resolve multi-scale phenomena such as turbulence. And across domains like additive manufacturing, we use simulations to resolve phenomena such as the complex multi-scale and multi-physics melt pool behavior in metal additive manufacturing. And across all of these domains, we use computer simulations to support design space exploration, predictive maintenance, and process optimization. However, the unfortunate reality of the situation is that physics-based simulations end up being incredibly compute expensive and end up bottlenecking several engineering workflows. The fundamental reason behind that is that physics-based simulations are built upon these nonlinear partial differential equations, such as the Navier-Stokes for fluid flow or the Cauchy stress equations for structural engineering. So once you have your equations down, what you end up doing is you discretize your domain into a series of triangles and quadrilaterals called a mesh. And inside each mesh element, you solve for your solution using a weighted sum of polynomial interpolants. Now the complexity comes in as follows. When you are resolving structures with fine geometrical features, you end up with meshes that have a large number of degrees of freedom. Therefore, you have a larger system to solve. Secondly, when you're solving for multi-scale phenomena such as turbulence, your time step size needs to be extremely short to resolve all the fine-grained features in your calculation. And what all of that ends up being is repeated large system solves that require high-performance computing architectures to execute. For that reason, there has been growing interest in neural signal representations that can learn to emulate physics from data. So as compared to the traditional finite element method, where you represent your solution as a sum of polynomial interpolants, a neural network, a multi-layer perceptron, which is the building block of modern neural networks, learns an input-output mapping via nonlinear transforms and implicitly stores the mapping in the weights of the model, which allows it to learn from data effectively. So in comparison to the classic finite element method, where you pay a large upfront cost per calculation, machine learning methods are very cheap to evaluate after you train these models. So you end up paying a large upfront training cost, but then you can deploy that learned model in time-critical applications. Finally, FEM is known to have very high accuracy solutions, but that comes at the cost of several years of dedicated solver development by teams of engineers and scientists. On the other hand, machine learning methods do not promise us extremely high accuracy, but they are indeed robust, as in the same method works on several different architecture choices. With these in mind, we'd like to divide the landscape of machine learning methods for computational physics along two axes. Along the vertical axis, we classify methods as those using a mesh-based signal representation and those who use a neural signal representation. And along the horizontal axis, we list methods as being either physics-based or data-driven based on their choice of inductive priors, as in whether they're using a governing system of equations or not. All right, so on the left end of the spectrum, in the world of physics-based methods, we have the classic finite element method, which uses a mesh-based solution representation. Whereas at the bottom, we have physics-informed neural networks that optimize the weights of a model against your PDE residual in its objective. Excuse me. Somewhere in between the world of data-driven and physics-based methods lies hybrid reduced order models, where the objective is to learn the structure of a solution from data and then use that to accelerate a physics-based solve. Finally, in the world of surrogate modeling, which is purely data-driven, where the objective is to learn the PDE solution operator purely from data, we have graph neural network-based methods that utilize the underlying graph structure of a problem. And then we have transformer methods that do not require any such graph connectivity information. So in this landscape, our contributions are twofold. First, we work in the domain of neural reduced order models, where we propose a fast and accurate method for latent space traversal. And secondly, we work in the domain of transformer surrogate models, where we propose a scalable transformer architecture for large-scale PDE problems. The outline of this talk is as follows. We'll talk about the first project on neural reduced order modeling. Then we'll move on to PDE surrogate modeling. And finally, we'll talk about our proposed work, which involves extending our surrogate modeling framework to transient calculations. Okay, so let's jump into the world of reduced order modeling, where the objective is to learn some solution structure from data and then use that to accelerate to physics-based solve. Okay, so just a quick 2-minute primer on model order reduction. The objective, to repeat myself, is to learn a low dimensional solution representation with data and then evolve that system with physics. So how does that work in practice? For the given partial differential equation, as you have over here, first we solve the system of equations with the high fidelity solvers, such as the finite element method. And of course, that employs a large number of degrees of freedom to discretize your solution. Then what we do is we assemble all of our snapshots and compress them jointly into a much lower dimensional representation. And once we have that done, we can essentially write an ordinary differential equations for the time evolution of the reduced states given in blue over here. So the cost savings in this are coming from solving a reduced system of equations as compared to solving a large system of equations with the finite element method. Okay, so how do we actually do this? How do you learn these manifolds? So for the same system of equations at the top, we are gonna denote our full order model or the finite or a high fidelity solver. We're gonna solve the system with our high fidelity solver, which is gonna discretize the solution with a large number of degrees of freedom, as illustrated by the curve in the at the bottom. Now this curve lies in a high dimension where every point in the curve corresponds to a different time, and each point is the set of degrees of freedom of that finite element solve. Okay, so what the linear proper orthogonal method does is it finds the best fit linear manifold to the data distribution, as in this trajectory. And as you can see from the simplified 2D example, it still leaves a lot to be desired between the yellow projection of the linear arm curve against the red curve. Now, recent neural network methods have been able to use nonlinear reduced order models to actually learn these nonlinear manifolds that can capture the salient features of your data distribution much more accurately. So in modern reduced order models, these architectures, these blue nonlinear manifolds are learned using convolutional autoencoders that learn to compress and decompress gridded data into compact latent spaces. However, when we apply the raw methodology to this convolutional autoencoder, we see that the model starts off very well, but it accumulates errors that lead to a really poor solution over time. As you can see in this figure, the convolutional autoencoder prediction deviates somewhat sharply from the ground truth solution over here. Okay, so upon investigation, we found the reason for this to be the following. So although the convolutional autoencoder does a great job at compressing the solution, as in the reconstruction loss is very small, we still have this issue of the physics solve deviating from the learned encoder projection trajectory in the physics solve process on the latent manifold. And this is evident from the intrinsic point of view. So I want you to imagine you jump onto this manifold and these are your X and Y coordinates. You would see that first, the red curve predicted by the encoder is somewhat convoluted. And secondly, the physics solve starts off pretty well, but slowly deviates over time, thus accumulating errors. Now, we propose a method called the smooth neural field reduced order model that is able to directly control the complexity of the latent trajectories. And you can imagine if we can make these latent trajectories extremely smooth and simple to follow, that would lead to a much more reliable solution. Our idea is to replace the original autoencoder workflow with a much more simplified workflow that gives us much more control. Let me show you how. So given the intrinsics of your PDE problem, we first learn a mapping between time and your latent trajectories, and we can force it to be an extremely smooth function. We do that by forcing that function to be a shallow MLP, and we apply enough regularization to make it basically linear, if not slightly worse. Once we have a reduced coordinates, we learn a coordinate neural field MLP as a decoder, which essentially maps our latent trajectory given in blue to the data manifold given in pink over here. And what that gives us is a supervised learning process where you are jointly optimizing the latent trajectories. Again, we've made them extremely smooth by design, and the data manifold at the same time. Okay, so you would expect this to be the silver bullet, but there is still one more problem when it comes to neural field reduced order models. Specifically, it is the following. When you regress a function, a continuous function using a neural network, what you would expect is that the model is not only that the model prediction actually matches the target function, but also that higher order derivatives of the neural representation match those of the target function. But that is unfortunately not the case, as you can see in this simplified example, where you can observe this high frequency noise just scattered all over the neural representation, and it gets exacerbated as you take higher order derivatives. So this ends up corrupting your solution. And if you are doing an online dynamics evaluation, you do need these higher order derivatives. So we propose two methods called SNFL and SNFWROM, explained in a minute, that are actually able to learn inherently smooth neural representations and thus solve this particular problem. So our first method is called smooth neural field with Lipschitz regularization. And the entire idea is to get a hold of the Lipschitz constant for an MLP. We essentially are able to approximate the upper bound of the Lipschitz constant of an MLP, and then we toss that into the loss function to minimize that directly. And what that leads to is inherently smooth solutions. To understand the second method, which is smooth neural field with weight regularization, what we did is we wrote down the expression for the first derivative of a neural signal representation. And we saw that these cosine W terms were popping up all over the place, and we matched them to the high frequency noise. Obviously, the bigger the W, the more the frequency. We know that. So what we do is we simply toss the W's in the loss function and apply L2 regularization to minimize their magnitude. This means that the neural representations we learn are inherently smooth because we are compressing these. We are literally reducing the frequency of these wiggles in the loss function. Awesome. So let's look at some results with this method. First, we'll look at the 1D Burger's equation at a Reynolds number of 10,000. And over here in the results, you can see the latent trajectories learned by the convolutional autoencoder proposed by Lee Kalberg, 2020, on the left-hand side, and the latent trajectories learned by our method in the center and on the right. And as you can see, the latent trajectories in the learned by the convolutional autoencoder are somewhat convoluted and they're hard to follow. You can see that the online solve given by the dashed lines often deviates quite significantly, even for the training test cases. On the other hand, the trajectories learned by our method, SNFL and SNFW-ROM, are near linear and they vary extremely smoothly. You can see that the dynamics evaluation or the physics solve matches the learned encoder trajectories near perfectly. Awesome. So we also solved the 1D Kuramoto-Shevashinsky equation, which is a fourth order partial differential equation. Now this problem, as we have set it up, is highly diffusive, therefore not the challenging problem from a classic reduced order modeling perspective. But when it comes to neural representations, this becomes challenging specifically because of the fourth order partial derivative. As we can see from the relative error versus time plots for a small time step size in the middle and a large time step size on the right, our method consistently maintains a low relative error as a function of time throughout the solve. So we are not accumulating errors even when we have a large time step. As compared to the convolutional autoencoder proposed by Lee Kalberg, which sharply deviates and leads to large error accumulations when you have a relatively large time step size. Okay, finally, we look at the 2D Viscous-Burger's equation at a Reynolds number of 1000. On the left-hand side, you can see a pseudo-color plot of the solution at the final time step. And in the middle, we have made an animation that traces the curve as it evolves along the diagonal y equals x. Now, as you can see, the curve, the ground truth prediction has a very sharp traveling shock that ends up accumulating at the end. You can see that the convolutional autoencoder and the POD-based method end up missing the shock somewhat significantly at the end. And that's obvious from the pseudo-color plots of the relative error and the plots of relative error versus time. On the other hand, our method SNFL and SNFW-ROM are able to maintain low error values throughout. And we are very happy to report that on this problem, we got a speed up of 199 times with a compression of from 500,000 degrees of freedom to simply 2 degrees of freedom. Awesome. So to summarize the reduced order modeling project, we have proposed methods for accurate derivative evaluation of neural signal representations, and we have proposed a method for fast and accurate latent space traversal for neural reduced order models. This work was published in the Journal of Computational Physics in 2025. Excuse me. And we also won a poster award at the World Conference of Computational Mechanics for this project in 2024. Okay, so let's take a break from reduced order modeling and move on to data-driven PDE surrogates, where the challenge is to learn a solution operator for a given partial differential equation purely from data. The way we do this is the following. So first, I want to emphasize that for any given partial differential equation, there exists the notion of a solution operator that maps some input parameter over here. In our example, it is the input geometry to the solution field. In our example, that's the displacement field. Right. So, but how do you actually go ahead and learn it? So, what you do is you train on a large number of samples from a distribution of these process parameters, of these geometry parameters, and you learn to predict your solution over that parameter space with the hope that your model ends up generalizing over that distribution of parameters. When you have that, you evaluate your model in an online inference stage by showing it novel parameter points and asking it to evaluating it for the corresponding solution field. Awesome. So the state-of-the-art neural surrogate models are all transformer-based neural networks which perform the following operations multiple times. The first operation is MLP that is applied to every point in parallel. And then the second operation is called attention, which essentially which involves every node attending to every other node in the mesh to update its value. So in a sense, this forms an all-to-all dynamically valued graph, which ends up being much more general than traditional convolutional neural networks or graph neural networks, because those two are limited by the connectivity structure of the input mesh. So, we do have a much higher level of generality, but at the same time, we do pay for that generality in a quadratic computational complexity. Specifically, you have n points that are listening to n other points, gives you n square message passing. Now, to analyze how deeply does that impact to analyze how much that impacts scalability, let's understand the method completely. So from the perspective of an output node, what I want to do is I want to listen to all of the input nodes in the domain. The way I do this, without going into a lot of detail, is by generating a probability distribution across all of my input nodes for every output node. And we put them together in an attention matrix given by A over here. So essentially, we are storing all the weights of this graph in an n-square matrix, and that's where the n-square scalability cost is coming from. We analyze the scalability of this method by testing it on different, by timing a forward and backward pass for a single attention layer on different sequence lengths or number of points. And we see that for a test case with 1 million points, a single layer of self-attention will take you approximately 20 seconds, which makes this method absolutely infeasible for evaluating on large PDE problems. So the goal for this section of the talk is to develop a scalable transformer model that can work effectively on large-scale meshes. But before we go there, I think it might be useful to take a step back and think about what are the limits on the communication patterns based on the physics of the problem we're looking at. So specifically, we are trying to solve differential equations, which are inherently local operations. So it makes sense that the graph or convolution-based method might work well. But I got to the bottom of it too soon. Anyway, so when we discretize the heat equation over here using a finite element or a finite difference method, we see that the forward pass is an extremely sparse, well-structured matrix, which kind of implies that the structure of communication should be local, if not anything more simple. However, what we are missing over here is that is the forward pass. What PDE surrogates are concerned with is approximating the backward pass or the solution function to the problem, which we know is inherently dense. So the the inverse of these simple structured sparse matrices is inherently a dense matrix, which somewhat indicates that any naive sparsification strategy may not work effectively for transformers, and that you need a principled approach to reduce the communication cost. So the question is n square scaling really necessary? Are we truly lost and do we not have any other options? I would beg to differ. And I believe what comes to the rescue is this unique property of partial differential equations or solutions to PDEs called smoothness. So what smoothness essentially says is that when you have 2 points in the computational domain and they are close enough to each other, their values should also be somewhat similar. And the closer they are, the similar their values should be. And that is demonstrated in the Navier-Stokes solution snapshot we have on the left, as well as its frequency, as well as its energy spectrum, where we can see that the higher wave number modes slowly decay to 0. What that essentially means is that all the fine scale large wiggles go to nothing. Anyway, so what does that say for message passing? If we are passing a message from the 2 green points to the blue point in the middle, what self-attention would want you to do is to simply pass 2 separate messages. But if we think from the smoothness point of view, we would notice that these points have a similar message that could be clubbed together into one message and then passed along that way. And then we could imagine doing this ab absurdum, as in arbitrarily many times over the entire computational domain. All right, so with that, we propose a method called FLARE, stands for Fast Low Rank Attention Routing Engine, which we divide into 2 steps. First, we have an encoding step where we introduce M latent cluster locations. M latent cluster tokens whose objective is to amass information from corresponding or matching input nodes via a dot product similarity. So the way this operation is done is exactly the same as vanilla self-attention, but with different inputs. So each latent node produces a probability distribution across all of the input nodes, thus getting these attention weights. And once you have these latent nodes put together, you do the exact same process, but it's mirror image. So what you do is that each output node would produce a probability distribution over all of the latent nodes, creating an n by m matrix in order to amass information from the latent nodes. Awesome. So that gives us our architecture with this really interesting butterfly-like procedure. And critically, we have been able to reduce the computational complexity from n square connections to 2mn connections, which gives us 2 benefits. The first benefit is that this method renders itself a low rank approximation, a low rank formulation of vanilla self-attention, which makes it extremely effective, extremely efficient for implementation. So much so that we get a 200 times speed up over vanilla self-attention when we attack problems with 1 million mesh points, which we do, spoiler alert. Awesome. So to test the effectiveness and the validity of our method, we test the model on several benchmark problems. For example, the elasticity, Darcy flow, and pipe flow cases in 2 dimensions, and the driver ML and a data set in 3D, and a laser powder bed fusion data set that we will talk about in a few minutes. First, we assess the effectiveness of softmax attention as a valuable baseline, because that's what we're trying to improve against. As you can see, softmax attention works pretty well for the 2D cases, but for cases with a large number of mesh points, we are not able to run it because it takes too long to solve because of the n square computational complexity. We test a wide range of other neural network efficient attention architectures as well. Among these, Transsolver stands out. However, we notice that for problems with the known structure or a regular mesh, like the Darcy or pipe flow cases, Transsolver was using a convolutional operation to essentially do some of the message passing in between the neighbors. Uh, and without that operation, its accuracy does worsen. In comparison to all of these methods, we are happy to report that Flare performs incredibly effectively on all of these test problems and beats every comparison model on every problem except the Darcy flow test case. Here's some visualizations of the Transsolver's, sorry, of Flare's prediction on the elasticity test case. As you can see, we are able to capture the high stress concentrations on the left and right hand side in both cases very effectively, and the error is approximately 1%, if not lower, everywhere. Same for the Darcy flow and the pipe flow test cases, where the ground truth and the prediction are near identical and the errors are minimal. Finally, we have generated a data set of laser powder bed fusion simulations where the objective is to predict the displacement field given an input geometry. And we are happy to report that the ground truth and the prediction match almost exactly, and our model produces extremely low errors almost everywhere. Finally, we'd like to let you know that in order to assess the scalability of Flare, we were able to train the model on a mesh with 1 million points. We got this data from the dataset generation process of Ashton et al., who have spent a considerable amount of time doing open form simulations of multiple car-like 3D shapes, where the task is to predict the pressure distribution over these shapes. In the plots down below, we have the number of blocks on the x-axis for all the plots, as in how deep the model is. And the y-axis has test, relative error, the time per epoch, and the peak memory usage from left to right. As we can see, that for all different values of m, which is the number of latents or the rank, we see a consistent consistent improvement in accuracy with the depth of the model, which is exactly as expected. Excuse me, sorry everyone, just hold on for a second. I think we had a technical issue. Anyone knows what happened? Yeah, maybe the projector died. That's so weird. Oh, no. Yeah.
Vedant, did you lose the Zoom or did you turn off the Zoom? Did you stop sharing or something?
I'm sorry, Krishna, I can't hear you. Could you speak up?
Did you stop sharing or because your Zoom is gone? I mean, you're on Zoom, but the sharing has also ended. Did you stop sharing?
Oh yeah, that might be the issue. Thank you. Are you able to see my screen?
Yeah.
Okay, so unfortunately, the folks attending in person are not able to see my screen at the moment. Yeah. So if you could give a minute, everyone in person would be able to log on to Zoom. Thank you for understanding. Okay. Guys, let me know when you are on. Good. Oh, we're back. Okay. Okay. So Krishna, Amir, could you confirm that you can see my screen? They confirm. Thank you. Okay. So we were talking about how Flare is able to scale effectively on this one problem where you were supposed to learn, where you learn a PDE surrogate on meshes with 1 million points. And as you can see from the plot of test relative error versus the number of blocks, as you increase the depth of the model, as you stack more blocks, you see an expected decrease in accuracy. And as you increase the number of latents M, or the rank of the method, you see an increase in accuracy as well. On the other hand, as you increase the number of latents, we do see that the compute cost goes up, but the peak memory remains the same. So in situations where memory is the bottleneck, we are doing extremely well. Okay, so beyond partial differential equation benchmarks, we're happy to report that Flare does extremely well on a set of long sequence length general transformer tasks, such as these recursive mathematical operations called list ups, where the model is supposed to solve these mathematical puzzles. On tasks such as text sentiment analysis, image classification, and also these visual logical problems where the model is tasked with finding out whether 2 points in this pixelated domain are connected by a line or they're not. You can see that among all of these, among all comparison models, Flare achieves the highest average score, indicating that this model is highly suited for these tasks. Awesome. So let me move on to the proposed work where we plan to extend our surrogate learning methodology via Flare to transient PDE problems. Let me motivate that first by talking about, excuse me. Let me motivate that first by talking about the laser powder bed fusion 3D metal additive manufacturing process. So in LPBF, what you have is a high-powered laser that selectively melts powdered metal onto a build plate to build a 3D printed part. Now, as it happens, because of the uneven heating due to the laser, these parts are incredibly prone to warpage or deformations. You can, in principle, solve the governing partial differential equations, which are a system of thermomechanical equations, to solve for this warpage in advance of the build process. But that ends up being compute intensive. It might take a day or two for these evaluations, so that cannot be deployed as an online or a design space exploration tool. So what we have done is we have created a data set of 20,000 laser powder bed fusion calculations where we simulate the entire build process from the build plate to the finished part. And our goal is to learn a neural surrogate model that can predict these deformations during the build. So we have to model the transient thermomechanical phenomena happening during this LPBF process. The end result, we hope, would be a valuable tool that could be utilized in design space exploration or design optimization of additively manufactured parts. All right, so with that in mind, we propose the following aims. Aim 1 is to enhance Flare for improved surrogate modeling. Firstly, we would like to increase the rank adaptivity of Flare by progressively adding latents during training. In aim 1A. Aim 1B is about developing a novel conditioning mechanism for Flare, which would allow us to manage transient calculations or transient surrogate learning tasks better. And aim 2 is to develop a decoder or a next token prediction version of Flare that would allow us to directly handle time series problems. Okay, let's get into aim 1A, which is to learn a rank adaptive version of Flare. Now, what we know from our previous experiment so far is that as you increase the rank or the number of latents in Flare, you get an increase in the compute time, which is expected because we are increasing the number of connections by increasing M. At the same time, as you increase the rank or the number of latents, you see a commensurate drop in error or an increase in accuracy, which is desirable. So FLAIR essentially gives you a trade-off between a high accuracy, high compute solution with a large number of latents, or a low accuracy, low compute solution with a small number of latents. What we want to achieve is some middle ground where we progressively introduce new latents into the training process, so we can get the benefits of a faster training run along with higher accuracy. The challenge in this process would be to preempt and design methods to minimize loss spikes or training instabilities that might happen with the introduction of new parameters into the learning process. Aim 1B is about developing conditioning mechanisms. But before we go into the details of what we propose to do, let's spend a second discussing what conditioning means and how it actually works. So when we're solving time series problems, our task is to learn a mapping from time, position, and a set of previous time steps to the upcoming time step, t+1 in this case. The vanilla approach is to simply pass all of these features as a single concatenated feature vector into your neural network model, which will implicitly update its provide a value that is conditioned on your time and the previous time steps. Alternatively, what many people have started working on is to learn a conditioning mechanism along with a token mixing or self-attention mechanism. And what this conditioning mechanism would allow you to do is to update your hidden state based on the conditioning information, in this case being time and the previous time steps. Now, the issue with the right-hand side is that you cannot mix token mixing or self-attention and conditioning. They have to be separate blocks. So what we propose to do is to create a unified block that can handle both of them in the same layer. And the key idea would be to use the conditioning information to modulate the token mixing process in FLAIR. So if we look at the plot in the middle, we have the standard FLAIR mechanism where the latent tokens given in pink modulate the token mixing process by selecting input tokens that have some similarity with the latents and then scattering that information back to the output. So there's a selective gather scatter operation going on. Now, if we were to condition these latent tokens on the conditioning vector as an update these latent tokens to take into account information coming from these conditioning vectors, we can in principle modulate this selective gather scatter process via the conditioning tokens. And that's our idea. So the good thing about this method would be that this would be linear in complexity in terms of both the number of conditioning tokens and the number of input tokens, both of which can be extremely large for large-scale time series problems. Our aim 2 is to develop a next token prediction mechanism for FLAIR. But before we jump into FLAIR, let's talk once again about how next token prediction works in standard transformer models. As you can see from the schematic, that this is somewhat similar to what we had with self-attention, but every point or every output token only pays attention to the input tokens from before that output token in order to maintain causality. And the way it is implemented in the training procedure is using this masking matrix that is essentially eliminating the impact of all future tokens. So this setup allows you to maintain the parallelizability of the self-attention algorithm while enforcing causality. So this is excellent for training. However, when it comes to inference or serving this model on an online problem, you notice that there are these exponential times, there are these several dot products in this evaluation. Now, as it so happens that at every time step, you get a new query vector, and then you have to evaluate all of these dot products once again. How many dot products there are? There are dot products equal to the number of time steps that you are at right now. So if you are at time step 1000, you have to store all 999 previous key vectors and value vectors in your GPU memory, and you have to keep them fresh. So this method not only has n-square complexity, but also a major memory bottleneck that limits its scalability. So with that in mind, we propose a decoder version of Flare whose key advantage would be that it does not have this this large memory bottleneck. Instead, Flare would only be able to Flare would only need to save O of m tokens in its online inference stage. Now this would be we would able to achieve this by using a procedure called the online softmax algorithm that will allow us to update our latent token ZT given information such as key and values from a new time step, and then we can use the standard standard decoding step for Flare. So this would give us a linear time autoregressive algorithm with the fixed memory footprint and a flexible latent capacity when we marry this with AIM-1A. The challenges with this task are the following. First, we would need to develop a bespoke training algorithm for this causal version of Flare so we can maintain the high throughput in training. And secondly, we need to write fused GPU kernels for both training and inference. Finally, we need to do extensive benchmarking and evaluation to make sure our model is indeed performant as compared to other decoder transformer models. The proposed timeline for this dissertation is as follows. AIM-1, I suspect, would take about 2 to 2.5 months, and I suspect AIM-2 would take much longer, mainly because you would have to, it is somewhat challenging and error-prone to write these GPU kernels. Finally, I plan to finish all of these aims and defend by the summer semester in 2026. So thank you so much for listening. I'd like to summarize this dissertation. In summary, we have worked on neural reduced order models where we have developed fast and accurate latent space traversal mechanisms. We have developed PDE surrogate models, which are extremely scalable and can be applied to large-scale PDE problems. And finally, we plan to develop transient PDE surrogates, extending the methodology proposed in Flare. All right, here's a list of my publications, and I appreciate your time and attention. Thank you.